A vector index cannot fix weak embeddings. E5 gives semantic search a retrieval-trained starting point before FAISS does the fast lookup. This is the pattern you'll be able to implement by the end, which indexes renewable snippets and compares recall against a baseline. I'm Professor Pi, teaching search and IR with simple Python. Semantic search often feels magical until you work with a real dataset. You run a nearest neighbor query and the top hit looks plausible, but it's not the right passage. That failure usually isn't about index speed. It's about embeddings that miss the intent. E5 is a family of sentence encoders trained with retrieval-style supervision, so its vectors already carry a matching signal between questions and passages. FAISS is the fast index that makes it practical to search many vectors. Put the two together, and you get a straightforward way to lift recall without re-architecting your stack. We want to test if swapping embeddings improves recall on a small, fixed set of renewable energy nodes. The goal is simple: get more relevant passages into the top two results. This is a small experiment. 2 queries, 5 documents, so we'll compare the baseline to E5 before thinking about scaling. Think of embeddings as short language summaries. If the summary drops keywords or intent, retrieval suffers. Retrieval-trained summaries keep that intent. FAISS doesn't change the vectors, it just finds neighbors fast. So the question is, does E5 place the right documents closer to our queries than the generic baseline? We'll build a tiny pipeline that does 3 things. First, compute baseline vectors and score a single query. Second, evaluate recall across 2 queries. Third, index both baseline and E5 vectors in FAISS and compare recall at 2. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we run a simple sentence transformer baseline to reveal which document best matches a recall-focused query. This snippet loads a generic sentence transformer baseline and shows which document the baseline thinks best answers our recall-oriented query. The list docs collects 5 renewable energy study notes that stay the same throughout the video. Base model creates the all-mini LM encoder, and we L2 normalize its outputs, so dot products act like cosine similarity. Multiplying the doc-emb matrix by the single query embedding produces similarity scores, and NumPy argmax picks the strongest candidate. The printed title names the highest scoring document and explains why the unoptimized baseline currently owns the top spot. We need a quick way to see how that baseline does across more than one question before we bring FAISS into the picture. This example encodes 2 evaluation queries with the baseline model to measure how often their relevant documents appear in the top 2 results. Eval queries pairs each textual query with the set of document indices we treat as ground truth for recall. We store normalized query M's from the same sentence transformer, then use a comprehension to grab the 2 most similar document IDs per query. Another comprehension computes the fraction of those 2 that overlap each relevant set, and we average those fractions across both queries. The printed number reports the baseline recall level and makes clear how much headroom there is for improvement. The baseline gives us a reference, but we also want to verify FAISS returns the same neighbors when we push the vectors through an index. This code builds a FAISS IndexFlatIP over the baseline embeddings to provide exhaustive inner product search for our queries. Dim captures the embedding size so the index matches the vectors exactly, avoiding any size mismatch. We add the normalized document vectors as float32 to the index. Then call IndexFlat.search to retrieve two nearest neighbors for each prepared query embedding. The helper hit doc maps the top result back to readable text for inspection. The printout confirms which passage FAISS returns first, showing the dense index mirrors the baseline scoring. Now we swap in E5 embeddings. These were trained with retrieval prompts to see how instruction tuning changes rankings. This snippet loads the instruction-tuned E5 encoder and formats inputs so its vectors line up with retrieval tasks. Doc inputs prepends passage to every document, following the fine-tuning format recommended for E5, while query inputs prepends query, so the encoder treats user intent differently from passages. We normalize the resulting vectors for cosine-style scoring, create another IndexFlatIP, add the E5 document vectors, and search with the new query embeddings for the top two neighbors. The printed title shows which passage E5 surfaces first, and hints at how the instruction tuning shifted the ranking. With both FAISS indices ready, we can compute recall at 2 and quantify the gain from swapping in E5. This example computes recall at 2 for both the FAISS baseline and the E5 upgraded index to quantify how many more relevant passages are captured. Rel sets pulls out the ground truth relevance sets so both systems are evaluated against the same targets. Two generator expressions calculate per query the fraction of retrieved IDs that overlap each relevant set, once for the baseline indices and once for the E5 indices. Averaging those fractions across queries yields comparable recall scores without adding new metrics. The final print highlights E5's recall and the absolute gain over the baseline, making the benefit of swapping embeddings explicit. Mapped to a real project, this compact experiment shows how swapping in a retrieval-tuned encoder can lift recall without changing your search code or index type. If the gain looks useful, the same steps extend to a larger corpus, more queries for statistical confidence, and production FAISS index types. Quick recap. E5 is a retrieval-tuned sentence encoder that better preserves query intent in vectors. Use it when you want higher recall without touching your downstream FAISS pipeline. One caveat: better embeddings help, but you still need careful props, solid ground truth, and representative evaluation queries. Next step: try tuning FAISS parameters, for example, different nlist or nprobe values, to trade off speed and recall while keeping the E5 vectors fixed. If short practical IR helps, subscribe and watch the IR videos.